This tutorial is on hybridization of orbitals and how they overlap to make covalent bonds. So this is hopefully going to tie in electron orbitals, electron configuration, covalent bonding, and Lewis structures. So so here's kind of how the theory goes, and it helps to explain how exactly do bonded atoms maximize the distance between each other in order to minimize repulsion. So hybridization of orbitals is meant to it's a theory meant to um, it's a theory meant to explain the valence shell electron pair repulsion idea. Okay, so it's trying to be consistent with the quantum mechanical model of electron orbitals, and to be consistent with the quantum mechanical model of electron orbitals. Okay, so SPD orbitals, they fuse together and they make hybrid orbitals, and this promotes the type of shapes that they make. And hopefully with like some pictures, I can try to explain that further. So the hybrid orbitals are used to bond with other atoms and to hold lone pairs. So what this means is the number of orbitals required to make a hybrid equals the number of effective pairs. In other words, if you have a let's say you have methane, for example. Okay, so methane, so it's CH4. Okay, and we know it has four effective pairs. Okay, so because it has four bonded atoms and no lone pairs, so it's four effective pairs. So carbon has, if we write its electron configuration, it's 1s2. So there's two electrons there. It's 2s2. There's two electrons there, and then 2p2. So out of its p sublevel, it's got two electrons there. So total valence that carbon has is two and two more. So total valence is four. And what carbon does is it makes it uses, so there's one, two, three, there's four total orbitals, okay, that it can use. There's an S, there's a P in the y-axis, there's a P in the x-axis, and then there's a P in the z-axis. So what it does is, in order to hold all four effective pairs, what it does is it uses a combination. It fuses together a P and an S, another P, and another P. So this brings us to a total of four orbitals which fuse together. Okay, so we say that the carbon here is so it doesn't, it's not an S, so we say that this carbon here is using an sp3 hybrid orbital to make all the bonds with hydrogen. So what is an sp3 hybrid? It's not an S and it's not a p orbital, so um, it's not one of these peanut shaped deals either. Okay, so it's not this and it's not this. It's more of like a hybrid. Okay, so it's kind of looks like it would look like this. So it's kind of like that. Why is it like that? Because of this. So it's like that in order to create a shape. So the sp3 hybrid creates a shape with where the bonded angles are 109.5 degrees. So from each bonded atom. Okay, so you have a hydrogen here, there's a carbon here, hydrogen, hydrogen, hydrogen. Okay, and what it does is it puts an electron here, and then hydrogen shares its electron here, here, and then so in this sp3 hybrid, carbon has an electron there, and hydrogen also has one electron, and then they share. So there's an overlapping of orbitals. Another electron here, and then hydrogen shares its electron to make the covalent bond. So the S shape doesn't work to make that maximum distance. The P shape doesn't work. Okay, the P shape doesn't work either to make this shape here. So the P doesn't work, the S doesn't work, so it creates this hybrid orbital. Okay, and the hydrogen by itself, this is just a regular S orbital, so it's just a sphere. Okay, so on to a couple more examples. So a sigma bond and a pi bond. So this a sigma bond is any single bond, a pi bond is any double bond. Okay, so bonding with atoms are called sigma bonds and are denoted with the Greek letter sigma. Okay, any double bonds or triple bonds are pi bonds and are denoted with a pi, the Greek letter pi. Pi bonds are not hybrid orbitals. So pi bonds are made with leftover orbitals after others have hybridized. So we'll look at a couple examples on when we show carbon. Okay, so hybridization and bonding angles. An sp3 hybrid looks like this. So I kind of showed that in the last slide. So it looks like this. And you have 109 degrees. This is an sp3. Actually, will look like this. Okay, and then the bonded atoms are 109.5 degrees. You can have an sp2 hybrid where it just uses one s, a p, and a p. This would be for 3 effective pairs. This one is 4 effective pairs. This one is 3 effective pairs. Okay, so an sp2 would end up being would end up looking like this. And the bonded angles are 120 degrees if it's sp2. And if you have an sp hybrid, it only has 2 effective pairs, so it only needs 2 orbitals to fuse together. It's an s and a p, and your middle central atom would have two uh, either bonded atoms or lone pairs. So the bonding angle here would be 180 degrees. And let's look at a couple examples to get an idea of how this works. So when do you have sp? When do you have sp2? When do you have sp3? So I'm going to go to carbon and single bonding. And this is the example I did earlier, actually. So I'm going to take carbon and do methane and show the sp3 hybrid. This is pretty much what I did earlier in the tutorial. So if you have carbon, it's going to have, so it has methane here. And it has 4 bonded atoms and no lone pairs. So there's 4 effective pairs. So if you ask what's the hybridization on carbon, you determine it by counting the effective pairs. That's all you do. So 4 effective pairs means you need 4 orbitals to make the hybrid. So it's made from an s, a p, and all 3p orbitals. So the carbon here would be sp3 hybridized. Okay. sp3 hybridized. Okay, so carbon and double bonding. So if you have, let's say, this molecule C2H4, it would look like this. Um, the Lewis structure would be a double bond between the two carbons, and the hydrogens would be connected like this. And so if we ask how many effective pairs are on this carbon, it would be three. One, two, and then three. So the double bond don't it just number of atoms connected, whether it's a single or double, doesn't matter. So that's how many effective pairs there are. So what this means is if there's three effective pairs, it requires three orbitals to make the the hybrid. So that's going to be um, it's going to end up looking like this. So your carbon will have a hybrid orbital here and here, and then another one here to connect. Okay, and then in each one of these hybrid, it's going to have an electron there awaiting a pairing with another atom. So this right here is an sp2 orbital, hybrid orbital. So all three of them are. Okay, on this carbon, this one is also sp2 hybridized. So this carbon will have an orbital, and this one also will have used three of its four valence for that. Okay, and it's going to have another valence electron there, and then it'll have another here. Remember, carbon has four, so there's one that we haven't used yet. Okay, and the hydrogen's attached with just regular, so it's an overlapping s orbital here that hydrogen is overlapping with. So this bond it's called a sigma bond because it's a single bond made with a hybrid orbital from the carbon. And notice the orbitals are overlapping to create these bonds. Okay, and then this hydrogen also just a regular s orbital. That's all it has, by the way, hydrogen. So it just has the single 1s electron, which it shares right there. And likewise on these bonds, you get a shared electron there, and then a shared electron there. Okay, so what's going on? There's an extra valence that this carbon that we haven't accounted for yet. Okay, so what happens is since we have so carbon, remember, it still has like an extra p orbital. So this is carbon's electron configuration. So there's two electrons there. On the 2s2, there's two there. And then on 2p, it has two electrons there. So we've used this, and this. So we've made an sp3 hybrid. I'm sorry, an sp2 hybrid orbital. But we still have one unused p orbital from carbon. So what it does is, in theory, is it's an extra p orbital. So this is not a hybrid. So we'll use a different color here. So this is an extra p orbital because we just these hybrid one that uses sp2, and both carbons actually have this, and there's an extra electron here on both. Okay, and they actually overlap, and my drawing isn't like entirely accurate here, but these p orbitals actually overlap in space. So I'm just going to use like a highlighter, and I'll make like a special note here that these make a pi bond is a double bond. So this is how the double bond happens. So this is the single bond. this is the single bond here, and then this right here is the second bond. That's the double bond. So this right here is this one. Okay, and then this right here is actually the second bond here. So so this pi bond is a double bond between two leftover p orbitals. And when you have this double bond, there's a special note to make that there is no rotation because of that extra p orbital. It doesn't rotate, so there's no rotation around double or triple bonds. Double or triple bonds. Okay, real quick on to the next example. So here we have an sp. So if we have this, for example, HCN, then you have the carbon here. So the Lewis structure will look like this, and the carbon and nitrogen is this carbon right here is going to be actually, let me use this example. So let's do C2H2 ethine. So if you have carbon, the Lewis structure will look like this. Okay, and this carbon we say is, it only has two effective pairs, 1 and 2. And same thing with this carbon. So two effective pairs means you only need two orbitals. So all you need is an S and a P. So we say that this is sp hybridized, the carbon there. Okay, so carbon takes an S and one P. So it's going to have two. So it has two leftover p orbitals. Okay, so it's going to have an electron there and there. Hydrogen bonds here, and then hydrogen bonds here using its regular s orbital. Okay, and I meant to do another, sorry, there's another carbon here. Okay, and then this carbon. Okay, it's hydrogen right there. And now we have two leftover p orbitals, so we'll put that here. So we'll put one of them like this. And then this carbon also has one here. Okay, and then another one here. Okay, so there's an electron here and here that share, and then there's one here, and then there's one here that share. Okay, so these will overlap, and then these will overlap also. So that's how you get the triple bond. So it's like these leftover p orbitals. So this right here is called a pi bond, and it has a second pi bond, second pi bond. So we say that this carbon right here is sp hybridized.